In this video, we are going to discuss optimization problems, which frankly, when it comes to working with differentiation, this is one of the major applications for why we do derivatives at all. Our learning objectives are based entirely on application problems. We'll look at a lot of word problems and try to create a function which we will have to find its maximum or minimum, its absolute maximum or absolute minimum. But in order to do that, we'll have to apply our differentiation techniques, whether that's product rule, quotient rule, chain rule, whatever. And of course, we'll want to be able to say, this is what our answer means. It doesn't really mean much if you can get an answer and not know why you get it or why you care or what it's good for. So we'll want to be able to interpret the results. The ultimate goal, again, is based in applications. There are a lot of situations where finding a maximum or a minimum is really beneficial, really desirable. Some clear ones, if you are a camera designer, if you could minimize the shutter speed, it means you've got a faster camera, which people would love to have for sports. And if you could maximize focus, well, isn't that what HD cameras are entirely about? Trying to create as much focus as possible? So for camera designs, maximizing and minimizing would be a piece that would play a role. A business owner would want to minimize their costs of business, but also maximize their profit. So basically, how can you go around maximizing or minimizing values? We are going to use calculus with finding the absolute or relative extrema. I would recommend that if you're a person who struggles a little bit with word problems, I would suggest that you pause the video and write all this stuff down at the top of your sheet. That way you'll have something that you can consistently reference when you're working on a problem or when you're working on an assignment. The general outline that we are going to follow is, number one, you have to understand what the problem is saying. It doesn't make any sense to say, well, I'm going to get my answer without understanding what I'm trying to do. You'll need to read the problem carefully and try to figure out as much about it as you can. Try to parse as much information as is available. You'll want to say, what are your variables? What are the parameters? What pieces are given? What are constraints? For example, talking about negative distance doesn't really make sense. And also, what are you trying to find? What is it that you're looking for? Try to understand the problem as best as you can. That way you can pick an appropriate strategy to tackle it. I know it's cliche, but for part 2, a picture is worth 1,000 words. If you can develop an understanding of the problem, use it to draw a picture. A lot of times, just by drawing pieces of it, you'll see some other connections. As you're drawing your diagram, of course, we're going to introduce some variables. Plug in some letters that say X is going to represent this side length. I'm using a dollar sign to mean money. Whatever variables you want, put some stuff in that will allow you to reference. If possible, we want this to be with a single variable. Now we know from related rates problems that we can use multiple variables. With Pythagorean theorem, we can have leg, and hypotenuse as 3 separate variables. And if we take the derivative, we wind up with 3 separate rates. Well, a lot of times more rates can mean more difficult. So if you can get it simplified down to 1 variable before you take the derivative, in many cases it will make the problem easier. But then ultimately, this is going to be an absolute maximum or absolute minimum problem. Optimization is always about finding the maximum or minimum. Whether it's an instance where in some of your earlier classes you would have just had this easy piece of you have a parabola and then you used formulas to say the peak of our parabola is this X number, it has a Y height of, and you interpreted them. Well, with parabolas, there's a formula that gives you the answer. We will not have a straightforward formula that says just use this one thing. but we will have a process using Calc to find the maximum and minimum. Maximum or minimum. So let's start here. A farmer has 2,000 feet of fencing and wants to fence off a rectangular field that borders a straight river. He does not need fence along the river. What are the dimensions of the field that has the largest area? Well, in terms of motivation, I think it's fairly straightforward why a farmer would want a large field instead of a small field. So, what's going on? What are some of the important characteristics that we should see? Okay, so 2,000 feet of fencing is talking about the distance that you'll be able to put up a fence. But then it's a rectangular field. So a rectangular field is telling us we've got a piece that is, let's actually grab this piece so I can do a real rectangle. Here's a rectangular field. But there's not a fence along the river, so here's our straight river. And you like how I'm putting it in blue, so we've got our water. Woo! Remind you of stuff. Yeah, we could potentially have the river be on the top. We could have the river be on the left. We could have the river be on the right. It doesn't really matter how you draw it. It's a valid question. Does the river have to be on the bottom? No, I just like putting my rivers on the bottom for some reason. Okay, so characteristics that we're noting. Some important things. You have a grand total of 2,000 feet in fence. So when we take side 1 plus side 2 plus side 3 for the fence, those three pieces will have to add up to 2,000. We also have area. We are looking at saying, when is there the largest area? So of course that's telling us we're going to wind up doing an area formula as well. Well, do we understand what's going on with the problem? Yeah, so far it seems like we've got a pretty good grasp of what's going on. We have our picture, but we could still go through and start assigning some variables. Some easy ones, we could say, here's our length, here's our width, which would tell us the 2,000 feet of fence is going to be the length plus the width, which I'm just going to write W plus W as 2W. And so we have some information that we know. We would also know that the area has to be length times width. Well, whenever possible, we want a single variable. We have these two equations. Let's plug one of them into the other. In particular, L from here, we'd be able to say L is equal to 2,000 minus 2W. So overall, our area is 2,000 subtract, well, sorry, that needed to be 2W times W, which we could then distribute across and say our area is 2,000 W minus 2W squared. Area is now a function in terms of the width of the field. And this is going to tell us the area of the field for any possible width. Well, what are some constraints that we'd have to think about? What is the smallest possible width you could have for a fence? Well, you really can't talk about having a fence of width 0, not for a rectangular field, so we know that the width is going to have to be bigger than 0. And overall, yeah, it definitely has to be less than 2,000. So if we wind up with answers that are outside 0 or 2,000, we're going to throw them out because they're not any good for our particular physical real-world example. At this point, We are now ready to turn the problem back into the stuff that we were doing at the beginning of our unit. We want to know, where does this piece have an absolute maximum, because we want the maximum area. Well, in order to get absolute extrema, remember absolute extrema can only occur in two or three different places. The endpoints are possible answers, but so are critical values. Critical values are going to occur when your derivative equals 0, or if the derivative does not exist. Well, since this is a polynomial, we know the derivative will exist. So the only thing we're really checking then are, we will need to know, if we have a width of 0, what is the area? 0. So that's not going to be very big. And if we have a width of 2,000, that's also going to wind up being an area of 0, which we could check by simply saying the width of 2,000 is going to be equal to, I wrote 20,000 there, 2 times 2,000 minus 2 times 2,000 squared. Well, 2,000 squared would be, okay. Let me back this part up. 2w squared, 2,000w. So we had 2000 minus 2w squared. Yeah, I lost my w, thank you. 2000w minus. Anyhow, the point that we would have for this is, we've got to find our critical value. So take the derivative. 2,000 minus 4w. And so the derivative is equal to 0, allows us to set up an equation that will find our critical value. So 4w equals 2,000. W is equal to 500. So there we go. The width of our fence for our critical value should be 500. The only possible values that we would have for our fence are 0, which gives us nothing for area, 2,000, which if we plugged in a of 2,000, 2,000 times w minus 2 times w squared. We're noting then that this is 2,000 squared minus 2 times 2,000 squared. That's going to wind up being a negative. And of course, negative area doesn't make any sense. So we know this constraint would have been even more messed up. But ultimately, what we're saying then is, this is the last possible value. The maximum area occurs when the width is 500. Did the question ask us what the maximum area is, or did it ask us what the dimensions for the maximum area are? To finally answer the question, it just said, what are the dimensions? We don't need to know the square footage of the actual field, we just need to know how big it is. So with this piece being 500, how big is the length? 1,000. And so here we have our dimensions. 1,000 feet by 500 feet. And to go back to what you were asking about, Scotty, would it have made a difference if we had it set up this way, so that we had the 1,000 and the 500? No, you still make the same fence. It's just a field on its side, basically. How much space do you want along the river? Okay, similar problem. A cylindrical can is made to hold 1 liter of oil. Find the dimensions that will minimize the amount of metal needed to manufacture the can. Okay, so what does minimizing the metal mean? We want to use less metal, and if you're talking about the metal that's used to make the can, you're talking about basically the shell of the can. That shell is surface area. To understand the problem, we have to look at this and recognize that this piece is talking about the surface area of our can, or the surface area of a cylinder. Well, how do you get the surface area of a cylinder? So to get the surface area of a can, surface area of a cylinder, we'd have to have 2 of the circles for the top and bottom. The area of the top for a can is pi r squared. And then we would have to have the height of the can multiplied by the circumference for the lateral area, which is 2 pi r. And so we wind up with this formula. I'm sorry, this is supposed to be an addition. So basically, we can factor out a 2 pi r, and a common formula that gets used for the surface area of a cylinder is that. Whether you build the formula, you look the formula up, somehow you've got to figure out we need surface area of a can. And we're noting then that surface area has 2 variables, the radius and the height. We want 1 variable. We are fortunate, though, that we are also told the volume, which we know is pi r squared h. The total volume is 1 liter. So if the volume is 1, we could divide by pi r squared and get h is 1 over pi r squared. Well, in order to do that then, we could now substitute that in to our formula and get 2 pi r squared plus 1 over pi r squared times 2 pi r. And this is our surface area of a cylindrical can that is guaranteed to have volume of 1. Let's simplify it. Our surface area depended on variable r. Well, 2 pi r squared. Pi over pi cancels. R over r squared is r to the negative 1. And so there we have our formula. What are the constraints on this? Obviously, the radius has got to be bigger than 0. And a radius of 1 would lead us to, okay, so 1 squared, that would be 2, oh, where were we looking? Strictly speaking, I'm not sure there is a constraint on the radius. Because if we start using a radius of like a millionth, like 0.00000001, it would just force us to have a really, really, really big height. But realistically, a radius of infinity doesn't really make sense. So we know that potentially there, if we were to do some more research, maybe we could find another constraint. But at the very least, we know that the radius has to be positive. Okay, so Jessica, coming back to what you said, take the derivative with respect to r. So that's 4 pi r plus a negative 2 r to the negative 2. And we want to know, where does the derivative equal 0? So we are now looking at 0 equals 4 pi r minus 2r to the negative 2, which would give us 2 over r squared equals 4 pi r over 1. Cross multiplication would then give us 2 equals 4 pi r cubed. Dividing by 4 pi would then give us 1 over 2 pi is equal to r cubed. So we wind up with a critical value. The radius would be the cubed root of 2 pi. Grab a calculator. Let's get a number. We know that this is an exact value, and hooray for exact values. But sometimes exact values are hard to visualize. So let's get a decimal approximation of this piece. R should be about, which is approximately 0.54. So something that at least seems reasonable. At least it's falling within our constraints that we said we needed to have. So there we go. Well, I would like to ask a question though. This is a critical value. Critical value could be a maximum or a minimum. There's nothing that tells us this is the minimum. Maybe this is the maximum area. We have not done and looked at that at all. Well, in order to check that, we've got a couple different options. Option number 1 is to say, take all our endpoints, take the endpoints of our constraints and our critical value, take each one of them and plug them into the surface area formula. Whichever one gives you the smallest height, that's the answer. Or you could just graph this piece on the calculator and say, let's look at it and see which one gives us the lowest. So we'll take a second, let's type this piece into our calculator and see what we get. And here is the graph of our function. Of course, I used x instead of r, but there we go. My window is going from 0 to 10 and from 0 to 10. So there we go. We can see on our graph it actually is a minimum around 0.5. So our answer then, find the dimensions that will minimize the metal. Well, we have figured out what the radius will be. Just plug in our answer for the radius and we will get the height of the can also. I'll leave that to you guys because of course that's just straight algebra to be able to plug that in and simplify. Find the point on the parabola that is closest to the point 1, 2. Okay, so what's going on in the problem? Closest is talking about distance. How do you get distance in the plane? Distance, we know, is basically the Pythagorean theorem, or more specifically, the distance formula. This is distance away from the point AB. Frequently the formula is written with x1, y1. I'm sure you've seen it that way as well. But what we are trying to figure out then is when is the distance the smallest. We want to minimize distance. Well, if we are looking at minimizing distance, that's talking about minimizing and taking the derivative of d. Except we've got x, we have y. We probably don't want x and y because that's two variables. Well, one piece that I would like to note, if we were to take this piece for x, we could divide by 4 and say x is equal to y squared over 4. That will allow us to do a substitution. Why wouldn't we want to just take a square root and say y is equal to 2x? Because y would also be equal to negative 2x. If we were to try to substitute in y equals 2x, it would give us one possible answer. But because of symmetry on a graph, we might actually have another answer as well. In fact, we should have another one. So we could do this two different ways. We could substitute in y equals 2x and worry about possible having duplicated or having a missing answer, or we could just substitute in y squared for x. Which way would you rather go? Okay, plugging in y squared for x, that will allow us to rewrite our formula. Distance is equal to x is y squared over 4. Our a value is 1. And our b value is 2. And so this is what we need to minimize. In order to help make this a little bit easier, if we minimize d and find the smallest value for the distance, that's actually going to be the same thing as if we find the smallest value for d squared. And so this is a piece that we will actually be able to look at doing. We could minimize this whole piece, which this would be, I want to write it taller so we can see it a little bit better. Y squared over 16 minus 1 plus y minus 2. Well, let's take our derivative. Let's find our critical values, and let's check to see what we wind up with. So we would have the derivative of d squared with respect to y. Well, what's our derivative over on the right? 2 times y squared over 16 minus 1 multiplied using the chain rule. This would be 2y over 16, which would, of course, is just going to be y over 8, plus y minus 2 times the derivative of the inside, which is just 1, so we won't write that. And so to simplify this a little bit, we wind up with, well, I'm looking at 2 times 2 over 16. 4 over 16 is going to be just y over 4 times y squared over 16 minus 1 plus 2y minus 2. And of course, we want to know when is our derivative equal to 0? Or where does the derivative not exist? Do we run into any problems with dividing by 0? Nope. With our y squared piece, we know for a constraint that we can't take the square root of any kind of negative. So that's a piece that we'll have to keep in mind. But when we solve this, we would have negative 2 y minus 2 equals y over 4 times y squared over 16 minus 1 So distribute across, negative 2y plus 4 equals y over 4 times y squared over 16 minus 1. And we could choose to multiply by 4 over y to cancel those pieces out, which would then distribute across to give us negative 8 plus 16y to the negative 1, which equals y squared over 16 minus 1. We could add 1 to both sides. We could multiply by 16 on both sides, which would be 70 plus 42, negative 112 plus 256 y to the negative 1 equals y squared. And so when is this part true? Progressing with what you had suggested, we could say over y, and then because we have a common denominator of y everywhere, we could multiply by y on both sides, which eliminates it and gives us negative 112y plus 256 equals y cubed, which we could then go through and say y cubed plus 112y minus 256 equals 0. And we're essentially saying, when is this stuff true now? Well, they do have formulas that will allow us to solve a general cubic. They're kind of bloody. We could also use our graphing calculator and just type this part in, y squared, type in the equation and tell it to solve for y, and it will give us some values. If we wanted to right away up at the beginning, as soon as we got to this stage, how we had negative 8 plus 18 or 16y to the negative 1 equals y squared over 16 minus 1. As soon as we got here, or actually, we could have come right up at this point. If you're going to use the graphing calculator, we could use the calculator's intersect feature to find our solutions. We could have typed this in, equation number 1. And we could have typed this in, equation number 2. And then just say intersect equation 1, equation 2. And it's not going to give you the exact value. It'll give you approximate values for your solutions, but if you're okay with being accurate to the nearest hundredth or the nearest 10,000th or however accurate you need to be, if that's okay, then we've got our ballpark figure. That's actually what we'd be able to do here. And although we're running a little bit short on time, we don't have enough, because class is running a bit short, we won't have enough time to actually go through and do that. But we've done enough of the calculator's intersect feature that I trust as a strategy, you're okay with doing that? Yes? Okay, everyone's telling me that they're okay with using the intersect feature. So wherever we get those intersected values, that will give us our critical values. Would like to remind you, I don't know what those critical values are going to wind up being. We could very well wind up getting value 1, value 2, value 3. We don't know right now how many places they intersect. It's possible from down at the bottom that there might potentially be 3 roots to this equation, so there might be possibly 3 different values. Up to. In reality, that won't be the case because of some other theorems, but when you get your possible values from the intersection, please make sure you do come back in, plug them into your distance, and actually see what the distance winds up being. Check the actual formula, and especially because we've got the given feature on our graphing calculators, we know that's a piece that we could get very quickly. Just given, have this equation typed in, given y equals type in your value of a, and it will tell you the distance. You don't have to do the full long algebra. You can take advantage of the graphic calculator to speed up the number crunching for you. Would like to back up and just check with our learning objectives. The idea of figuring out the function that you will need. Does that make sense? The process after you create the derivative, or after you create your function, you will have to calculate the derivative so that you can find the critical values. Once you have the critical values, you will have to find the absolute maximum or the absolute minimum. Please remember, when you're looking for the absolute maximum or minimum, you could have the endpoints. Do not forget to check them because they do happen sometimes. Endpoints with the restrictive criteria do sometimes influence it. Or you can find critical values. It's all the absolute maximum, absolute minimum piece that we were working on previously. Once you figure out where your absolute maximum or minimum are, then you would come back and say a piece like here. The dimensions of 500 by 1,000 give me the dimensions of 500 by 1,000 will give the largest possible field. That's an interpretation. The dimensions of radius equals 0.54 and the height that would equal will give us the smallest can. Well, the smallest can would also be the cheapest can to build. So finally, create the function, take the derivative and get your absolute maximum or minimum, write up a sentence that says, here's what this stuff means.